Everybody. Hopefully you can see my screen.
Yes, Nikos, we can see your screen.
Okay, thank you. Well, I'm going to talk about the geotechnical hazard module, which in fact is a geotechnical hazard assessment focused on liquefaction and landslides. And this is a joint work from the Department of Civil Engineering of the Democritus University of Thrace by the team which is with the names that they are written already here, presented here, and Professor Kostas Papatheodoru from the International Hellenic University. Well, in the event of a strong earthquake, usually we have a part of damages which is related to ground failures. And this in our project is named as earthquake triggered geotechnical hazards. We focus only on two of them, and mainly at the regional scale, not a local scale for the time being. Liquefaction and landslides, as I said, liquefaction susceptibility and hazard assessment, and landslides hazard assessment. The geotechnical module will be incorporated into the radar system as it has been substantiated already in Greece at different pilot regions wherever we had earthquake-triggered landslides and liquefaction phenomena. Now, regarding the susceptibility part of liquefaction, the most critical parameters which are taken into account are the following: the geological age, the depositional environment of the sediments, and the distance from the water body, no matter if this water body is a river, a lake, or a seashore. And this, whenever we have a peak ground acceleration more than 10% of G. Now, regarding the evaluation of the liquefaction hazard, we adopted a method which has been proposed about 10 years ago by Holder and his colleagues, computing the probability of liquefaction on a regional scale and enabling surfacial geologic maps. We pass from liquefaction probability curves, in fact, into liquefaction hazard maps, which is actually what we need. Now, the probability of surface manifestation of liquefaction upon this methodology depends on the peak ground acceleration, on the depth of the groundwater table, on surface geology, and of course, on earthquake magnitude. The equation used to calculate the probability of surface manifestation of liquefaction phenomenon is this one, where A, B, and C are parameters that depend upon the type of geological sediments and the depth of the water table. According to Holder et al. Methodology, the water table depth was taken at 1.5 or at 5 meters depth. Now I'm going to present an example of this methodology at a regional scale. An example implemented in the Hellenic area, and it has to do with the historical earthquake of magnitude 6.5 at the area of Aegion at 1861. Well, what we can see now is a map of probability of surface manifestation of the liquefaction at the Corinthian Gulf by this scenario of the earthquake of 1861. And what we see with the chromatic scale is the probability. Wherever you see the green is less than 10% probability of surfacial manifestation of liquefaction. And the red, which is around the AO area, is more than 50% probability of occurrence, which means more likely liquefaction. This is the kind of output that we will have by this methodology. On the other hand, in the case of the USGS, if we take as an example the Croatian earthquake 6.5, which occurred at the end of the year 2020, and based on another methodology of statistical character, where peak ground velocity is needed, the VS30, which means the mean velocity of S waves over the 30 superficial meters, the mean yearly rainfall, the distance from the seashore and the river, and the depth of water table. This is the kind of map that we can expect, which means this is the probability of liquefaction occurrence. And according to the chromatic scale, we can see where it is most probable and less probable that liquefaction can occur. On top of that, we also get an estimated surface subjected to liquefaction and an estimated population exposure to liquefaction. Now, if we move to the second geotechnical hazard assessment, meaning the landslide hazard assessment on the regional scale, this we all know that it is a useful tool that can support decisions regarding the strategic planning for disaster prevention. But we believe that it can also make part of the radar system. And landslide hazard maps can be used to estimate the potential risk and prioritize areas in order to apply the preventive measures, and also guide where slope stability analysis should be done. In case of a seismic event, it will provide us a near real-time map where likely landslides are expected to have occurred, as we know that soil and rock instabilities are considered as a potential damage. For this reason, we adopted two different methodological approaches, one based on statistics and the second one belonging to the category of the physically based methods. The implementation of these methodologies is feasible under the existing conditions in the pilot implementation areas of the project. We adopted the method, an empirical method from Nowicki et al., which has been proposed in 2014, and which combines shaking estimates with landslide susceptibility proxies such as slopes, surface geology, and climate parameters. This method has been improved 4 years later by an updated model, and which refers and regards the near real-time assessment of seismically induced landslides. And the best fitting model is this one presented here, where you can see that the peak ground velocity, slopes, lithology, land cover, compound topographic index, meaning about which is an indirect index for wetness, are used, and all the coefficients A to G are solved within this regression. The predicted probability of landslide occurrence is the following one, as you can see, provided that we have already calculated in this way a parameter T. An example of implementation of this methodology, which is already adopted by USGS, is on the Indonesian earthquake of 6.2 on 2021, where based on the latest statistical model of Jesse et al., using the peak ground velocity, the CTI index, soil wetness, lithology and land cover and slope, what we get is a map like that, where we can see by the chromatic scale, in fact, the probability of earthquake-induced landslides. And also, on top of that, the estimated surface subjected to landslide hazard and the estimated population exposure to landslide hazard as well. Finally, the physically based landslide hazard assessment methods are based essentially or solely, I would say, on slope failure processes. So there are methods that engineers are, I would say, feel more at their ease. They can apply over large areas, let's say then regional scale, provided that geological and geomorphological conditions are pretty homogeneous and that landslide types are relatively simple. In physically based models, the probability of occurrence of a landslide is expressed via the factor of safety and the values obtained by the factor of safety. What we have adopted for the time being is the infinite slope model, which is a suitable model and worldwide used model for shallow earthquake-induced landslides. The driving equation for earthquake triggering effect is this one, where I will just point here that the A used here is the PGA value, the peak ground acceleration value. And I have to underline that this method has been successfully tested in a pilot implementation area in Greece in regional and local scale, but only for rainfall triggering effect, not for seismic triggering effect, in the framework of a previous project named SINET-NATHAS, which was ended by 2015. My last slide is an example of this project. This is a map, a part of a map, and this is a detailed part of this map where you can see that we got the factor of safety calculated by the infinite slope model. The red part is about 1 or less than 1 safety factor, meaning that we have a landslide, the slope is not stable, and the green means that we have a factor of safety more than 1.5, meaning that the slope is stable. What you see in black open circles are the field observations where this method has been validated. And as you can see, we got enough red colors all along this area, and the circles that you can see are the pictures that are just beneath, where you can see by yourselves that there are slopes that are really unstable, and the infinite slope model was able to depict them. This is the left part is the implementation at the regional scale, and the right part is the implementation at a local scale that the infinite slope model has proven to be able to depict slopes at a local scale that were stable and some others that were not, along an axis which is very close to the border of Greece and Bulgaria. But I have to underline that this has been achieved not only due to the infinite slope model, but with the help of the high level of accuracy provided by geoinformatics and remote sensing technology. Thank you very much for your patience.